Hello world. Um, in today's video, we're going to continue solving problems using Newton's first law of motion as I have promised in the previous video. So today I want us to look at a set of problems that we are going to solve. But before we do that, I would like us to go back to a scenario that we have seen when we were busy drawing our free body diagrams. So was the scenario that we had in the one of the previous videos, and I would just like us to use this scenario to solve Newton's first law problems. So it says that an object of mass 2 kilogram is sliding down at constant velocity, so it's clearly moving down a rough, so it means that we have friction because it's moving, that will be kinetic friction. Down a rough inclined plane, down a rough plane inclined at 7 degrees, so it means that this is our theta, this is our angle of inclination. Okay, so the first question normally is define or state. I'm going to say state Newton's first law of motion in words. And this question is normally worth 2 marks. Um, Second question I am adding, I want us to draw a free body diagram. Please pause and draw it for yourself. I know we've drawn it before. Just draw it for yourself. I'm going to make this 3 marks. Normally when we say you need to draw a free body diagram and we say 3 marks, there's this rule that we as teachers have made it up. It it's it's not always true though, but it gives you a sense of how many forces you're supposed to have. So normally if they just say draw a free body diagram showing all the forces acting on this object, if they say 3 marks, it means that we expect to have 3 forces. So basically one force is equivalent to 1 mark. But you need to use this rule with caution, because sometimes it's 1 force 1 mark versus understanding. Because if then they're going to say draw a free body diagram showing all the forces acting on this 2 kilogram block, but you need to draw it to scale, then the scaling is going to have its own marks. You might find that the free body diagram might end up being having marks greater than 3 because the scaling now has its own marks. But we're going to look at that problem at a later stage. Number 2, I want us to draw the free body diagram. Number 3, I want us to calculate the normal force. Number 4, the last one, I want us to calculate the kinetic frictional force. And let me just perhaps edit a final question. I'll add it later. So Newton's first law, when you state or define, you are required to use the examination guideline so that the laws do not lose their meaning. The second one, the free body diagram, pause to try this out for yourself, but we have drawn this in the past. So where the axes meet, you draw your object. Remember, draw the axes before you draw your forces. And then we have normal force. We have kinetic frictional force, which is opposite the direction of motion. And lastly, we have the weight. Fk is along the x-axis, no problem. Normal force along the y-axis, no problem. The problem is the weight because it's somewhere in between those axes. So it means we need to draw the components of the weight. Remember to draw the components of the weight. The parallel component is always facing down the slope. This will be my parallel component. Perpendicular component is always opposite to the normal. Okay, we only have the components if the surface is inclined. Okay, so that is much better. Don't draw the weight together with its component, because then they'll see that as having extra forces, because you need to understand that these components combined, they represent the weight. Okay, now that is our free body diagram. I think in grade 11 we can get away with this, drawing the components instead of the weight. And then the second question says calculate the normal. Remember, we have said that this is moving with constant velocity. What it means is F net is equals to 0. F net equals to 0 means that sum of the forces along the x direction is equals to 0. And it also means that sum of the forces along the y direction equals to 0. Whether we use this one, number 1, or we use number 2, it depends on where the force is located. Because we are trying to calculate normal force, we can clearly see that normal force is along the y direction, so we are going to opt for this one. So sum of the forces along the y direction, because this is moving with constant velocity, should give us a value of 0. Along the y direction, I'm going to take that as the positive direction. So I have positive normal, positive for direction, plus, because when we talk about net force, this is sum of, that's why I'm putting a plus in the middle, plus Fk, but the Fk, oh no, my apologies. What am I doing? Along the y direction, my focus is on the y direction. I have the normal and I have the perpendicular component. So there's the perpendicular component, but it's in the negative direction. Those will give me 0 if I add them together. So we have a normal minus perpendicular component, because positive times negative is negative. I should get a value of 0. But how do we calculate the perpendicular component of the weight? Remember, we have said that to calculate the perpendicular component of the weight, we can use a weight cosine of theta, where theta is the angle of inclination of the slope, this one over here. How do we calculate the weight? That is mg. Weight equals to mg. The mass it was given, it's 2 multiplied by 9,8. The answer there will be 19,6. So we have 19,6 cosine of theta. Let me try to grab my calculator and see what we get. 19,6 cosine of 7 degrees. That is 19,453. Then I can substitute in. Make sure that you don't leave this in your rough section. As part of your solution, write it somewhere. This will be normal minus 19,453 equals to 0. Therefore, if you transpose, the normal will be 19,453 newtons. Okay. And then the second one, which I want us to calculate, that is kinetic friction. Remember, I said we have a formula to calculate kinetic frictional force. To calculate kinetic frictional force, number 1, you can either say Fk is equals to mu k multiplied by the normal. Or number 2, you can use sum of forces. Sum of forces along which direction? Along the x direction, because kinetic friction appears on the x-axis. If you sum them, we said that will be equals to 0. So you have to decide on which one you're going to use. If you look at the first one, do we have the normal? Yes, we just calculated the normal. We are trying to figure out what Fk is. Question is, do we have the coefficient of kinetic friction? The answer is no, because we have too many unknowns. We cannot use the first equation, so the one which will be appropriate will be the second one. So sum of forces along the x direction will give us a value of 0. So we always need the free body diagram to answer these questions, so that we can clearly see and pick the forces along the x direction. Along the x direction, I have the parallel component as well as Fk. These are the forces I'm going to be adding together. Before you do that, because they are pointing in opposite direction, we need to pick a positive direction. And I said for future references, I'm going to be taking direction of motion as positive. So it means I have positive parallel component, plus minus the kinetic friction. The plus is the fact that this is sum of forces. The negative there is for direction. I need to get a value of 0. And then if I transpose Fk, I have that Fk is equals to parallel component of the weight. How do we calculate parallel component of the weight? Remember, we have said that the parallel component of the weight, I'm going to write it here in pink so that it stands out. Parallel component of the weight will be weight sine of the angle of inclination of the slope. The weight we found it, we said it was 19,6. We have sine of theta is 7 degrees. If I punch that on my calculator, I have 19,6 sine of 7 degrees. Sine of 7, not 1. I'll just try again. 19,6 sine of 7. 2,388. So this will be 2,388. So I can sub in there. Make sure you include all those calculations as part of the solution. Okay. So that will be our answer. Just took that and substituted there. And now the last question I said, let us try to calculate the coefficient. Oh yeah, I didn't write the last question. The last question is, let us calculate the coefficient of kinetic friction since we do not have it. To calculate it, we are going to use that equation over there. Let me just get rid of this. Okay, so I'm going to use Fk equals to mu k multiplied by normal. I want to calculate the coefficient. Do we have the Fk? Yes, we do. That is 2,388 equals to, I'm going to leave mu k because I don't have it, multiplied by the normal. The normal was 19,453. And then you divide both sides by 19,453. And then if you do that, you'll find that your mu k, remember we predicted that it should be greater than 0 but less than 1, and it is indeed greater than 0, less than 1. And remember that the mu k is unitless. What I want to bring to your attention from this problem, unlike the previous one, we have said that for this particular problem, specifically this problem, to calculate the normal force, we said sum of the forces along the y direction equals to 0. What did we have? We had the normal plus minus the perpendicular component equals to 0. And then if you make normal the subject of the formula, you find that it is equals to the perpendicular component. But I want us to go back to yesterday's problem, which we had. This was the problem from yesterday. From this problem, when we calculated the normal, we first started by drawing the free body diagram, the weight, F, and then we said we had Fk. To calculate normal, we used the same formula, F net along the y direction equals to 0. We said normal minus the weight equals to 0. If you transpose, normal was equals to the weight. I need you to please note that this is not always true, because we can clearly see it that in yesterday's problem, normal was equals to the weight. But when we come to today's problem, the normal is equals to the perpendicular component. So to avoid making mistakes, please stick to this when trying to calculate the normal force. Because you will see that this is not always true, and this is also not always true. And we're going to see that we can have a different expression for the normal when we look at more problems from today. But this one, I think I'm going to give this problem to you guys so that you can try it out. But I am just going to look at this one for today. Okay, this question says Simon is hanging at rest from a loop. So there's Simon there. Hanging at rest. Very important. What does it mean? It means that F net equals to 0, which is attached to a ceiling by 2 ropes. We hear 2 ropes. When you hear ropes, immediately tensional force should come to mind. The rope make an angle to the horizontal ceiling at 500 and 600 as shown below. I think that that is a mistake there. It's supposed to be the ropes make angles to the horizontal ceiling of 50 degrees. So the angle is 50 degrees to the horizontal of the ceiling. The other one is 60 degree to the horizontal of the ceiling as shown in the diagram below. The tension in P that is given there, remember the assumption we made was that the tension was the same throughout the rope. That was in the previous video. And when we look at Q, we don't know what the tension is. Okay. The first question says define the term resultant vector. Remember, you state according to the examination guideline. And what I indicated earlier on was if the question is like this, it's out of 19 marks, then half of the marks should just be a giveaway. Because this is 19 marks, half of 19 is 9,5. 9,5. But we don't give half marks here. So what this means is approximately 10 marks are for free. Let us see where we get those 10 free marks, the definitions. Over here, we are defining a resultant vector. You should know the definitions by head. We have the 2 marks. We are down to 8. There they say define the term weight, another 2 marks. Now we are down to 6. Let us try to find low-hanging fruits, those questions with 3 marks. It says draw a vector diagram. Okay, so we're going to represent these forces using arrows. That shouldn't be difficult. You have another 3 marks. So 3 more marks to go until we get to 10. It says write down the magnitude of the resultant, another hanging fruit. So 2 marks. Let us see how much we have. We have 9 marks here. Now we need 1 more mark. And then it says calculate the magnitude of the horizontal component of the tension. It depends where you're going to get that free mark of yours. You can either get the free mark somewhere here, or you can try your luck and get it anywhere else, because you still have 2.7, 2.5. You also have 2.4. So over here, but 9 marks straight away, it is for free. You just need to find a mark for yourself. A resultant vector, please pause and try that out for yourself, is a single vector having the same effect as 2 or more vectors combined according to the examination guideline. Then it says draw a vector diagram showing all the forces acting on Simon. Remember, Simon is somewhere here. Simon, where was it? Simon is hanging from a hoop. So Simon is somewhere there hanging from a hoop. So I'm going to first draw the forces on the diagram. If Simon is hanging there on the hoop, the first force, we have weight. Simon has mass. He must have mass because Simon sounds like a person. So we're going to have the weight. We have rope Q. We're going to have tension. The tension is along the rope Q, away from the object. The object is Simon. So there will be tension. So I'm going to specify it so that it does not look like there's tension here. So I'm going to call this TQ, meaning the tension in rope Q. And then we also have another rope. So we're going to have another tension. So it's a long rope P away from Simon. So that will be tension in rope P. So they say they're looking for a vector diagram. So I'm going to be using these arrows to represent these vectors. And because it's hanging from rest, Simon is in equilibrium. Opposing forces acting on him are balanced. What I'm going to do here, I'm going to draw a closed vector diagram. Okay. So for 2.2, I'm going to draw my y-axis. We don't have a surface here, so there's no normal. And then x-axis. I'm going to put Simon there in the middle. So this will be the weight. And because I said I'm going to draw a closed vector diagram, I'm going to draw these vectors tip to tail, head to tail, tail to head, sorry. From the tail all the way to the head. Once I get to the tail of the weight, I can draw another Cartesian plane so that I can be able to draw TQ. And there's something that I want us to bring to our attention. So we were given the angle between, this will be the angle between the horizontal line and the tension. If I draw another horizontal line over here, the ceiling is horizontal. So this is horizontal, this is horizontal. So clearly these are parallel. I'm going to apply maths here. So if these lines are parallel, it means we're going to have the Z angles, the alternating. Are they alternating? Yes, they are alternating angles. It means that the angle over here will be equals to 60. Remember how I defined the 60-degree up there? I said that was the angle between the horizontal and the tension. So if I bring it somewhere here, it's between the horizontal and the tension. So I'm going to draw my set of axes. There they are. I'm going to draw them in green. And there's the tensional force, TQ. And what I'm saying is between the horizontal and the tension, that angle needs to be 60 degrees. And then finally, I can draw the last one, TP. And then I'm going to include set of axes there. There's TP. This is TP. Let me just move this label here. TQ. Gonna remove these axes. Maybe they're gonna help me. And then let us look at this 50-degree angle now. The 50-degree angle is between the horizontal and what? It's between the horizontal and the tension T. So if I include that set of axes somewhere there, it's between the horizontal and T. So that angle there is 50 degrees. Or I can put it somewhere up there. Let me put it up there. Remember what I'm saying? I'm saying it's between the horizontal and the tension. So that angle there is 50 degree. But we are mainly interested in the angles which are inside the triangle. Okay, I want us to go back here. So if we look at this, we said these are the vertical, these are the x-axes, they are perpendicular to each other. So it means that the angle from there all the way to the x-axis, it should be 90 degree. If this is 60, you can try to find this angle here. So this angle, which I represented in dot, plus 60, they should give me 90. If I solve for the dot angle, that dot angle will be close to 30 degrees. It's very important to include the angles inside the triangle because in future they're going to help us to solve the problem using the properties of triangles. So that green angle, I found that it was 30 degree. I can apply the same thing to find this angle because the horizontal and the vertical, they're at 90 degree. It means that inner angle there will be equals to 40. And then I can figure out this whole big angle over here. So I had this, that is 40. I can use sum of forces inside a triangle to figure out that third angle there. That third angle will be 40 plus 30 plus that big angle. I'm just going to call it A. This should give me 180 from maths, sum of angles inside a triangle. If I solve for A, you will find that A will be 110 degrees. So this will be 110. Remember, this is TP. And I'm going to remove the label of W. I'm going to put it there. So if we look at this triangle, there's only one side of it which is known, which is TP. We know that TP is equals to 500 newtons. And I don't know if you've done this in maths. If there's only one side of the triangle that is known and two angles known, then you can use sine ratios to find either this side of the triangle or that side of the triangle. Remember that the length of the side represents the magnitude of the weight. The length of this side represents the magnitude of the tension in Q. So you can use sine rule, but I think for today, instead of using sine rule, I'm just going to be using component method. And once we are comfortable, I'm going to introduce the sine rule. Okay. And then the other question says, this will be my closed vector diagram. And when you draw a closed vector diagram, include at least two angles inside the triangle so that you can get your full marks. And then it says, write down the magnitude of the resultant force acting on Simon. We said that will be 0 Newton. A resin opposing forces are balanced. Opposing forces are balanced. And then the other one says, calculate the magnitude of the horizontal component of the tension in rope P. Because I am avoiding to use too much mathematics, this was for the answer in 2.2. I'm going to make my life easy. I'm going to come back to the free body diagram. I'm going to use the free body diagram to answer the question in going forward. So to use my free body diagram, I need axes, y-axis, x-axis. And if you look at carefully from the forces on the diagram, the weight is the only one which is along the y-axis. Let us look at TQ. TQ is going to be somewhere here. TQ is somewhere between the y and the x-axis, so it needs to be resolved. If I resolve it, I think I've spoken a lot about drawing the components, so I'm just going to draw them out. So for TQ, I'm going to have the y component, TQY. I'm going to have the x component, TQX. And then for the tension P, I'm going to have y component pointing up. This is TPY. And then I'm going to have TPX. So this will be more useful now because I can clearly see collinear vectors. In 2.4, what are we trying to calculate there? We are asked to find TQX. Remember, we have said that F net was equals to 0. It means F net along the x is equals to 0. It also means that F net along the y will be equals to 0. So to find TQX is along the x-axis, so we are going to rely on this formula. On the x-axis, how many forces are there? It's TPX and TQX. So you need to pick a positive direction. I'm going to take right as positive. So we have F net along the x equals to 0. So we have TPX in the negative direction plus TQX. If you sum them, you should get 0. Question is, how much is your TQX? I need us to go back to the diagram. If you go back to the diagram, remember we said that that angle there, the 50-degree angle, was between the horizontal and TPX. So it means the angle is there. Why did I write TPX? That is TP. The tension in rope P. If we resolve it, I'm going to resolve it in yellow. We have TPX. We also have TPY. These components are perpendicular to each other. If you define sine of theta, sine of 50, theta is 50, that will be the opposite, which is TPY. That is TPY divided by hypotenuse, which is TP. If you define cosine of 50 degrees, that is adjacent to the side next to the angle, that is TPX divided by TP. So we can clearly see that the x component is taking cos. If you cross multiply, it will tell us that TPX is equals to TP cos of 50. So there we have it. We can bring it here. So we have negative for direction. We have TP. We have TP cosine of 50 plus the x component of the tension in Q. But how much is TP? The tension in P, it was given to us. That tension was 500. So let me punch my calculator. We have 500 cosine of 50. Okay, I'm going to put this here. So it tells me that I have negative, come back, comma, 393 plus TQX equals to 0. If you transpose the 321, you're going to have that TPX will be equals to positive 321,393 Newton, and that will be our answer. And I can see that it was given 2 marks. That is fine. And then the other one says calculate the magnitude of that's the one we were answering. It says calculate the magnitude of the tension in rope Q. Okay, so if we come back to this diagram, let me tidy this. If we come back to this diagram, we said this was the tension in Q. That is what we are looking for. And we said this was TQX as drawn on that free body diagram. And then we also have TPY. Let me move the labels there. This is TQ, TQY. Let me draw this a little bit shorter. In the components, we have said that they're perpendicular to each other. So the X component, I realized there's a mistake. It's supposed to be QX. This one we have calculated it. We said it was 321,393 Newton. So if you like, and this angle we said it was 60 degrees between the horizontal and TQ. If you like, you can use trigonometric ratios to solve this one out. We are trying to find the hypotenuse of this triangle. So let us see if defining sine works. Sine of 60 degrees, that is TQY, the opposite over the hypotenuse TQ. Let us see. Do we know what TQ is? That's what we are trying to find. Do we know TQY? No, so this will not be useful. Let us try out the other trigonometric ratio. Let us go for cosine of 60 degrees. Cosine of 60 degrees will be adjacent, that is TQX divided by TQ. Do we know the value of TQX? Yes, we just found it. So this will be cosine of 60 degrees equals to TQX, which is 321, 393 divided by TQ. Then you can cross multiply and solve for TQ. Okay, so let me just do it somewhere down here. So if you cross multiply, you're going to have TQ multiplied by 321,39. Yay. No, I'm cross multiplying, right? This is this multiplied by that. Okay, let me redo it. So we have cosine of 60 degrees multiplied by TQ being equals to 321, comma 393. Then you can divide both sides by cosine of 60. Divide by cosine of 60. And I expect the tension in Q to be greater than 321 because this is the hypotenuse, the longest side of the triangle. So let us say, calculator, 321, comma 393 divided by cosine of 60 degrees. Really? I don't trust it. 321, comma 393 cosine of 60. Much better. I think I'm gonna oh, it said multiply. This has to be divide by. Yeah, this is more like it. Now this answer I trust. 642, comma 786. 86 Newton. Okay, done. So there we have it. That is the magnitude of the tension in rope Q. And then it says define the weight. Remember, the weight is the gravitational force that the earth exerts on an object. And finally, it says calculate the mass of Simon. I want us to go back to our free body diagram because it's the one that is helping us to solve these problems. This is the simplified free body diagram up here. If we look at the free body diagram, a free body diagram shows the forces acting on an object. And when we talk about mass is not a force. So we need to identify the force that will have the mass in it. And that force is the weight, because we are saying to calculate the weight, that is mass multiplied by gravitational acceleration. So it means if we can find the weight, we'll be able to calculate the mass of Simon. But looking at the weight, where is it located? Along the y direction. So we need to sum forces along the y direction for this problem. So for this problem, we need to sum forces along the y direction, and that will give us 0. Along the y direction, what do we have? We have TQY, the first one. We have TPY, and then we have the weight. I'm going to take up as positive. So we have TPY plus TQY plus the weight, but it's in the negative direction. It's pointing down. That should give me 0. Do I have TPY? Let us see. TPY, we can calculate it. Remember, TPX looked something like TP cosine of 50. It means that the y component will take sign. So this will be TP sine of 50 degrees, and the same is applicable to TQY. This will be TQ sine of 60. If I transpose the weight, I bring it to the other side, that will be close to the weight. So the weight is equals to TPY was 500. This is 500 sine of 50 degrees plus this one, we just found it there, that is 642, 786 sine of 60. Let me employ my calculator here. The sum is too long. So I have 500 sine of 50 plus 642,786 sine of 60. Because of the learner there, it's going to give me incorrect things. That's supposed to be 500 sine of 50 plus 642,1807,785 sine. Work with me here, calculator, because I don't have my manual calculator. So it keeps on writing wrong things for me. Let us do this one step at a time. So we have 500 sine of 50. It says 383,022 plus the second part. Second part is 642 sine. Nope. 642,786 sine of 60. That is 556,669. This means that the weight will be equals to, let me see, I have 383,022 plus 556,669. So I have the weight as 939,691 Newton. Now I can find the mass. We know that, I'm going to bring it here, the weight is equals to mass multiplied by gravitational acceleration. This one I have found, 691 equals to mass multiplied by 9,8. Therefore, the mass will be equals to, Simon must be having a large mass. So that is 939,691 divided by 9,8. No, not too bad. Average human being. 0.886. Remember, the units of mass are the kilograms. So there we have it. Those are the two problems that I'm going to be looking at, but I'm going to give this one to you so that you can try it in your own time. And in the next video, I'm first going to start by going through this particular problem. That's it from me for today. Thank you.